back to the second lecture. So it seems that we made a lot of progress all of a sudden. We were talking about tree level, and now we have a proposal to all loop. Okay, so that's a big progress. This proposal is due to Bernziks and Smirnov. This is the answers that are roughly that I sketched a little bit. It's essentially this one loop result with this replacement of G squared by gamma cusp, which we know through integrability. This by the standard pair equation, which I've mentioned. If you're interested in understanding the origin of this equation, I could explain it to you after the lecture or any day next week. Okay. And this we know is the least we can do to agree at least with the infrared divergences, which are precisely controlled by this correspondence modulus dimension. But is it enough for describing the rest? I mean, okay, the infrared divergent piece is well understood, but the final part is something which is not captured by this end-waving argument or explanation that I gave you. So now we are entitled to ask the question whether BDS was right, whether we already finished, whether the job is already done, and so the lecture should terminate, or not. That's why this is what Aldai and Maldacena, Fernando Aldai and Juan Maldacena, decided to investigate a few years after BDS pushed forward their proposal. So, of course, BDS, they were smart, so they proposed their answers after making a lot of tests of it. In particular, for 4 points, they did some computation up to 3 loop, which means that if you want to test their prediction for 4 gluon scattering, you actually need to do 4 loop computation. So needless to say that it is quite difficult. I don't know if it has been done since their paper appeared, perhaps. So what you could do to reduce the number of loops is to look at more legs, 5, 6, and so on. So in this case, as far as I know, BDS did some, so generally did a check at 1 loop, but beyond 1 loop, it was not obvious how to do. When you start having more gluons, of course, you have a lot more diagrams to consider. The integrals are much more complicated. So it will look like a big miracle if they are right for higher points. Okay, but who knows? I mean, this theory, n equal to 4 in the planar limit is exceptional, so maybe there are a lot of miracles that we should expect, and this could be one of them. So Aldai and Maldacena, as I said, wanted to test this proposal, but they didn't want to do some 4 loop computation or to investigate 2 loop contribution to a 6-point amplitude. So they decided to attack the problem from a different angle. So one test that you could do, that is in principle totally independent of what BDS did, is to see whether their ansatz is robust at strong coupling. Okay? So when the tough coupling becomes very large, you are very far from the regime of applicability of any perturbative techniques of the gauge theory. And so if you manage to prove by some method that the BDS ansatz is correct in this regime, that would be strong evidence that it has to be true somewhere in the middle. It's a bit like controlling the 2 hands of a flow, you know, weak coupling, strong coupling. If you find the same thing in the 2 limits, or roughly the same thing, or at least what is predicted by this guy, then it's almost a proof. Okay? For some people it will be a proof, but not for everyone. Anyway, so Aldai and Maldacena wanted to do this analysis, and of course if you want to do this analysis, you need to use some information about the strong coupling regime of this theory, and this is where string theory enters. So you all know the claim. The claim is that you can study n equal to 4 as strong coupling by using string theory. Okay? So the string theory setup is that you have space, which is ADS5 times S5. So here you can forget the S5, it's not going to be relevant. Okay? So we have a string which is living in ADS5, whose metric can be written as follows. Okay, where this is just our original metric for the gauge theory, which is Minkowski 311. I guess I'm using signature plus minus 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 in case you want to know. And then we have this extra coordinate C, which is the so-called 5th dimension or holographic direction. Which essentially resolve the various scale of the theory. So changing Z is like changing the scale at which you look at the gauge theory. So this is saying that you can think of your gauge theory local observable, okay, to live on the boundary of this space, which is at Z equal to 0. This is where this factor blows up, okay. So when you want to compute something in this theory, you put some boundary condition here from the gauge theory. So let's say you consider a Wilson loop. Okay, so you define some contour, okay, which is the contour of your Wilson loop, okay, and then you want to find the string theory description. And the claim is that the string theory description, in this particular case of a Wilson loop, is to look for a minimal surface which ends on this contour at the boundary. So is it something that Nadav explained already, or no? So this is due to Maldacena, and the claim is that it is an accurate description when this quantity, square root of lambda over 2 pi, which is the same as 2g, I often switch between these two coupling, okay, is large. The reason is that this is the tension of the string. So when it is large, the fluctuation of the string are small, and so we can rely on a semi-classical description. So here what you are instructed to do to compute this Wilson loop from the string theory is just to compute the path integral over the fluctuation of the field 1. These are embedding coordinates times exponential of minus square root of lambda over 2 pi, which plays a role of inverse h bar, if you want, for the one-sheet theory, times the non-Bugoto action, which is just square root of the determinant of the induced symmetry. Okay, so these embedding coordinates are subject, defined like this, plus y1 squared dot y4 squared. They live in a 6-dimensional space. This is the same space as introduced by Osborne. Okay, and to restrict to ADS5, we impose this condition. Okay. So you compute this. You can solve for this identity if you want. You can then try to compute this path integral. Of course, there is a lot of things which I'm hiding here because it's a superstring theory. There is this S5 in. There are the fermionic mode of the string, the fermionic direction that should be included. So computing this path integral is, as you might guess, something very challenging. But in the limit that we are interested in, this is essentially controlled by the saddle point. And given the boundary conditions that we are fixing, our object is only exploring or living in ADS5. It is exploring the full space quantum mechanically, but it is living in ADS5 from this specific observable. So it is dominated. It is dominated by exponential of minus square root of lambda over 2 pi times the area of the minimal surface. Okay. So this is a prescription due to Maldacena and other people. It will be the second group. Okay. And for instance, if we wanted to apply it to something which we care about immediately, it will be, for instance, for the computation of this cusp Wilson loop. Okay. So is it true, for instance, that if I choose my contour to be this cusp, which we were looking at before, is it true that I will recover divergent area which has this double logarithmic divergence that I expect? And if yes, is the coefficient in front of it related to the strong coupling value of the cusp anomalous dimension? And the answer is, of course, yes. Okay, as you might guess, we're not going to prove that ADS-CFT is wrong today. So what you do is that now the solution lives in an ADS-free subspace. Okay, so you can forget about the transverse direction here. So we just have x, t, and z. Okay, and I'm trying to draw what the solution looks like. So here is my contour and the boundary. And then here is my string. I think that looks like this. Okay, so the string is pulled inside the bulk because of this gravitational potential. Okay, so it wants to live as far as possible from the boundary. Okay, but it cannot be all the way to what is called the horizon, the equal infinity, the horizon of the space, because it is attached to the boundary. Okay, this is the prescription. And you can plot this solution if you want. It's very simple, it is just this expression. Okay? That's a minimal solution. And you can compute the induced metric. And the induced metric is just given by minus 1/4 du plus over u plus square plus du minus over u minus square, where the u plus and u minus, I write them, but are just this Lycan coordinate t plus minus x. And if I go to this exponential form, u plus exponential to sigma and u minus exponential to tau, this just take a very familiar form, d sigma square plus d tau square. So you see that in appropriate variable, the induced metric here is nothing else than flat space. So this is just Euclidean two-dimensional flat space. And this you could, again, probably have guessed just based on what we said before, that are the symmetries of this object. So you want something that will be invariant under shift of sigma and shift of tau, okay, which is this two rescalings that you can do by combining boost and dilatation together, rescaling of u plus and u minus. So this is essentially what you expect. Based on this symmetry, what you have is essentially a Poincare symmetry in two dimensions. And so this is no surprise eventually that we are getting this simple expression. And from it you can immediately understand that indeed, if I try to compute the area, which will be the integral of d sigma d tau, what I will find is infinite. I mean, if you try to compute the volume of an infinite space, what you get is infinite. Okay? So you need to put some regulator, and if you do this, you find in the exponent this string tension, which is just a measure of the density of energy of the string, times some delta sigma and delta tau, which are the cutoff. Okay? So I want to integrate over a big volume. I have delta sigma and delta tau to be large. I cannot take them to be infinite because I will get just infinity. It will be nonsense. Okay? So in practice, what you do is that you don't want to go up to the bulk. If you go up to the bulk, it's like taking sigma and tau to go to infinity. So you put some cutoff here. You integrate up to some z uv, roughly speaking, and that behave essentially like that. Okay? So if you re-express it in terms of the original coordinate, this means that it's a double log divergence. So we recover precisely what we found in the gauge theory, namely that the object that we care about, so sorry, this is just multiplication, could be misunderstood, is just some constant 2g times this double log. And this is precisely what we, so is a 1/4. And this is precisely what we were expecting if gamma cusp is equal to 2g as strong coupling. And this happens to be true. Okay? Gamma cusp can be shown to be just measuring the density of energy, and this density of energy is just the string tension. So we are kind of happy. We see that we are on the right tracks. Again, the string theory is producing exactly what we were expecting. So now what we want to know is whether we will get that lucky when trying to compute the finite part of the amplitude. Okay? But to compute the finite part of the amplitude, we need to understand what is the prescription for computing an amplitude in this space. So how do we prepare gluon state, and how do we scatter them? What is exactly the prescription? So this prescription was rather intuitive. You put the local degrees of freedom of the theory here, and you look for whatever object extend it naturally into the bulk. For scattering amplitude is perhaps less clear. Essentially what we want to do if we go to the Penrose diagram of our space is that we want to prepare some state here with some momentum, P1, P2, and annihilate them in the future. Okay, again with some momentum. So what does it mean for the string theory? So let's to perhaps understand what is going to happen. So here is some process. So this process is not something which is localized at any point. So there is no natural local definition of our object in the bulk as a source for the bulk theory. So to understand better, what we would like to do is to wrap this object on a cylinder. So this is essentially working in this global coordinate. So we wrap the picture roughly the same as before. That was Poincaré patch. It's just a small piece of the full embedding space of the string, which is better viewed as a cylinder. So here is my Poincaré patch at the boundary. I identify this point and that point. This is my conformal compactification. Okay. And then I look at what I'm doing. So I'm putting something here and here, which from the bulk means setting the problem at infinity on this light sheet, which cuts the cylinder. So ADS is the inside of the cylinder. Inside the cylinder we have ADS 3 here. The boundary is just my boundary theory, which I've wrapped around. And then I cut the cylinder like this with two light sheets. Okay? The inside here, what is inside the bulk and bounded by these two cuts, is precisely this Poincaré patch. It's just a change of coordinates that mark one to the other. But the cylinder extends this picture all the way from minus infinity to plus infinity. So this part here is what is called the horizon. It is z equal infinity, if you want, in this picture. So we understand that when we want to specify a boundary condition for an object like this, a non-shell object like that is coming from the past and going to the future infinity, we should put the information not on the boundary but at the horizon of the space. So the picture is that we have our space again, my boundary. I should take the horizon. So let's move just the horizon a bit closer to us. This can be done by introducing what is called a brain. This is an extended object that allows us to set up some boundary condition for the string, some new boundary condition for the string. So it is put at some infrared z, which is very, very large. Okay. And now what I want to do is the usual string theory type computation for open string, which means that we put some vertex operator on this brain. Okay, let's put 4 of them. These are meant to be at infinity. And then we look at the worldsheet with a disk topology, which go through all these vertex operators. Okay? This is the open string scattering in this problem, but of course, we put the boundary on this brain. The open string are attached to this brain, but the worldsheet can live in ADS. So the main difference between what we are doing here and computation in flat space is that the string of course knows that there is a gravitational potential, and in particular the worldsheet wants to be pulled in one direction or the other, depending on the energy of the scattering process. So this is essentially what we want to do, but it's not clear how we can do this. I mean, how do we construct this kind of vertex operator in this complicated background and so on? It's not something which is very well understood already for the problem of the clustering problem that was mentioned by Kolya. It is not known how to do it along the traditional line of string theory in conformal gauge and so on. So people had to go to this Lycon gauge and deal with this massive integrable theory instead. And this way they could understand the 2-point function. Okay, but how to generalize this to 3-point function and so on is something which is not yet fully understood, even though there are tremendous progress in this direction. And here is also a kind of problem that we don't know yet how to even set up properly. Okay? But Alda and Maldacena, they were smart and they noticed that there is a huge simplification that one should have in mind, which is that when we do such a scattering process attached on an infrared brane like that, which is characterized by a large value of z, the proper momentum of the string here is not, for instance, P4 for this guy, which is the momentum measured by this theory, but P4 times this gravitational potential, which essentially means that this string carry very high energy. So the kind of scattering process that we are interested in is a scattering process in which it's a hard scattering process at fixed angle. Okay? All the momenta are rescaled with the same factor, which is taken to be very large. Okay? And this kind of scattering process was known for a long time to lead to certain simplification. Already in flat space, Gross and Mendel understood that if you want to compute this kind of scattering process, you don't really have to, set up, use the full machinery of the string S-matrix program. You define very accurately your vertex operator and so on. You can rely on the semi-classical approximation. So what happened is that the part of the vertex operator which is relevant for the computation in this regime is essentially this tachyonic part of the vertex, exponential pi mu x mu in flat space. Okay? And once this p is very large, this, if you want, act directly at the level of the exponent in the path integral and source, if you want, a classical problem. So if you want to understand the behavior of scattering amplitude in this regime, you can directly solve a classical problem in the worldsheet theory. So you need to understand what is this classical solution that you need to construct, which means what are the boundary conditions that correspond to this vertex, and then you just have to solve this set of classical equations. And if you do it in flat space, you will easily reproduce, for instance, for the 4-point, you will easily reproduce a very well-known behavior for the hard scattering limit of the Venezian amplitude. You know, this product of gamma function whose arguments are given by this Mandelstam invariant S and T, which become exponential of S log S plus T log T and so on. But now this exponent you will get not by doing some painful computation, but just by finding the appropriate classical solution to your problem. So this is saying that we should expect to be able to solve this problem because it is essentially semi-classical in nature. It is no more difficult than this one, it's just that the boundary conditions are a bit more tricky. We need to fix the momenta, the incoming momenta. And here there is an additional trick that Alda and Maldacena found, which is that what we can do is, because it's a purely classical problem, what we could do formally is perhaps to redefine our coordinates and map it to yet another problem, which is mathematically equivalent. And the step they took is formally what is called in string theory as a T-duality transformation. So I assume that you are a bit familiar with it. So when you have a string which is compactified on some torus or cylinder, okay, you have two types of states. You have those that wind around this direction. They are typically, when the tension is low, they are typically very heavy. And there are those who are just carrying some momentum, like the Kaluza-Klein. Okay? So this is one feature of string theory, that when you compactify it, you get Kaluza-Klein excitation, like in local field theory, but you also get this winding mode. Okay? And the T-duality is a transformation that map the radius of this to the inverse of the radius and exchange winding and momentum mode and Kaluza-Klein mode, roughly speaking. Okay? And Alda and Maldacena say that even though there is no compact direction in our problem, ADS is not compact at all, okay? There is no cycle in it, we can still formally use the very same transformations that exchange these two descriptions of string theory. It's something that you can just write down mathematically, and what they observe is that if you do it, ADS map back to ADS. So the T-dual picture of ADS is ADS itself. So you can exchange our original problem into a new problem. And what is this new problem? Well, you can start understanding that if we have a momentum, and now this momentum becomes a winding, What is a winding is the condition that the string should end on this momentum. Okay. So now the momentum becomes a locus, a line where the string should end. We have 4 momenta in the simplest possible case, which form a closed contour. Okay. And one more thing that we should do if we want to literally map ADS to ADS is to perform a z goes to 1 over z inversion, which is somewhat reminiscent of this inversion of radius here, which means that our problem, which was originally defined in the infrared, is now defined in the UV, meaning pretty close at the UV, which is very small, which means pretty close to the boundary. So what we are getting is exactly the same as for Wilson loop, but with this funny contour, which is made out of the momentum of our scatter particle. So it's a polygonal closed contour, with each edge being like-like. So the solution to our problem is find the minimal surface ending on this polygonal Wilson loop and compute its area. And something that we immediately recover, and which is very satisfying, is that we will get in this picture UV divergences coming from all these cusps. Okay? Because locally the solution around this cusp is no more than the solution that we've constructed here. So we will indeed recover that our object has divergences which are associated to this cusp, which is something that we immediately understood before from the amplitude point of view. Okay? But what this picture is telling us, it is telling us something more. It is telling us that not only the divergences here are encoded by this kind of Wilson loop, but also the finite part. So if you now compute this minimal area, this minimal surface area, using some cutoff, like some UV brain like this, to avoid going all the way to the boundary, you will find a piece which gets large when you are trying to put this EUV to 0, and behind it there will be a finite piece, and this finite piece is the string theory prediction for the finite part of the amplitude. Okay? So this is Aldair-Maldacena prescription, and what Aldair-Maldacena could do in practice is to find explicitly the solution for 4 gluons, meaning for 4 cusps. The reason is that 4 cusps and a single cusp are essentially the same, if you think about it. If we take this picture, let me perhaps just, for this picture I can draw like that. The single cusp is something like this. There is one cusp here, sorry, which is visible in this Poincaré diamond, okay? And there are, but the string itself extends beyond this point and touch these 2 lines. And this guy here are identified. So you see that the full object has actually 1, 2, 3, 4 cusps, but only one is visible in this patch. Okay? So this solution and the solutions that control the scattering of 4 gluons are the same, up to conformal transformations that map us from the Poincaré patch to the global coordinate. So once you know it, you can perform whatever conformal transformation you want that will bring this 4 cusp inside a given Poincaré patch, okay, which is possible in R31, and you will compute the area of this minimal surface. Okay, and this way, Aldair-Maldacena could verify that the prediction by Baird-Dixon and Smirnov is correct upon replacing gamma cusp by strong coupling value for the 4 gluon scattering. So that was quite remarkable. So it was the first evidence that the Baird-Dixon on that is reliable even beyond recoupling, even beyond the regime where it was tested to some extent. But they also provided in a follow-up paper some arguments that will invalidate it for a higher number of gluons. So this is a very simple argument, so I will give it to you now. The idea is that they didn't know how to solve the problem with 5 or 6 gluons, because then you start looking at more complicated surface. They are no longer reducible to the single cusp. Okay, there will be more freedom, and it's rather non-trivial to solve the classical problem and find explicitly the minimal surface, even though later on people understood how to actually solve entirely the problem without even finding the minimal surface using the integrable techniques, the integrable structure of the worldsheet. So they could write some TBA equations that unfortunately I don't have time to give you that control this problem. So the problem is essentially solved nowadays. But at the time Alda and Maldacena found some contradiction with BDS. It was not known how to do it. But what they did is very intelligent. They say, let's consider a case where we have a very large number n goes to infinity of gluons. And let's choose our cut such that they essentially accumulate along a rectangular contour, like this. So you take a lot of curves, and then you take a turn, and then like this, and then back again. Okay? This is in principle something which describes the scattering of a lot of gluons as strong coupling. And you can imagine that if you take a suitable scaling limit, this will eventually reduce to a gentle rectangular contour for Wilson loop. Okay? So the minimal surface ending here should eventually at large n, and if you don't look too closely to the boundary, be approximated by the minimal surface ending on this rectangular contour. Okay? And this solution is known. This solution was constructed and was solved. And it has nothing to do, if you compute its area, on the finite piece of the area, let's put a prime, it has absolutely nothing to do with the limit when n goes to infinity of the strong coupling version of BDS. So from this kind of argument, Alda and Maldacena understood that the BDS ansatz has to fail for some large enough value of n. They could not say precisely for which value of n it will fail, but they knew in advance that it would have to fail. Okay. So we are back in business because now we understand that BDS did a great job, but they missed something. So there is something that has to be computed. There is something which is not immediately predicted by our expression, and which should, in the end of the day, accommodate for the fact that Wilson loop in ADS are more complicated than what one could infer from BDS. Okay?
Sorry, this rectangle is not lighter.
No, the rectangle itself can be purely Euclidean. Okay, I'm just approximated it. It looks like a very complicated approximation, but I'm just making a kind of discretization of it using this like zigzag contour. Okay. But even though there is a kind of even though we could perhaps be disappointed or not that BDS is not correct, we gain something here through this analysis. We gain the intuition that perhaps in this theory, in n equal to 4 super Young means computing scattering amplitude is the same as computing the vacuum expectation value of some like Wilson loop. And this is what is known or called nowadays a scattering amplitude Wilson loop duality. So the claim is that this WN that we are desperately trying to compute and that describes this amplitude is the vacuum expectation value of a Wilson loop whose contour is made out of the momenta of our scatter particle. Okay? So this is literally true at strong coupling because of what I said. What is not obvious is that it should hold true at weak coupling or beyond strong coupling, even perturbatively at strong coupling. The fact that it has a chance to be true perturbatively at strong coupling was discussed by several groups who gave a definition at the quantum level of this T-duality, so they could make sense of this T-duality and in particular give some evidence that it is not an anomalous transformation. So meaning that this is a symmetry of the path integral, of the string path integral, which should hold at least, I mean at best, or at worst, sorry, at any order in the strong coupling expansion. So perturbatively a strong coupling. People also consider weak coupling. Several groups consider what happens at weak coupling. And they found through explicit computation and also other kind of argument that this scattering amplitude Wilson loop duality should indeed be true in this theory in the planar limit. So in the planar limit, this is a kind of bonus relation that we get, and which allows us now to formulate the problem in a completely different way using this Wilson loop. And something that some of you might immediately understand is that what we are gaining here is additional symmetry on our object. Because this Wilson loop, of course, is subject to conformal transformation. There is a usual conformal symmetry that transforms this Wilson loop. And one particularity of having a polygonal contour is that if you perform a conformal transformation, it will map back to a polygonal contour. Okay? So this class of objects are invariant. Okay? It's not like if you take a random contour, even if it is straight, you perform a conformal transformation, it can become circular and so on. So, and if it is more involved, it can become almost everything. It's not easy to characterize the orbit of a given contour. But here it's simple. When you do transformation, you get an object of the same type as before. But these conformal symmetries that act on this object and constrain its form, okay, is not the same as the conformal symmetry that was acting on the scattering amplitude. So what we gain here is a second copy of the conformal group, which has some overlap with the original one. For instance, dilatation on the scattering amplitude side mapped to dilatation on this side as well. But for the rest, for the conformal generator in particular, it's not true. So we gain a double copy. So we have a dual conformal symmetry in the game. And in fact, if we include supersymmetry, we have a dual superconformal symmetry. And these two groups, they actually do not commute. And if you try to force them, try to commute them, one with the other, you find that you generate yet a new type of symmetry, so a new generator that was not there at the beginning, and that keeps going forever, and that gives rise to what is called the Yangian. So there was a lot of excitation around this. So first on this discovery of superconformal symmetry by the group of Chomsky, Drummond, Hand, and Sokachev, and then by the understanding that this is equivalent to a Yangian by Plevka, Hand, and Drummond, I think, and others probably. Because you know that for many people, Yangian symmetry is a signature of integrability. Okay. So that, through this a bit long historical perspective on the problem, we now understood that indeed there should be integrability in the problem. And now the question is how to set up this problem in a more integrability friendly way. How to compute this Wilson loop. Okay? Any question about this? No? Okay, so now we really enter the program of this lecture. We'll have to shorten some part. So what do we learn, for instance, by using directly this conformal symmetry? So first, how would you characterize this object in the conformally invariant way? How would you do? Any suggestion? No. So you will do the same as what Osborne did during his lecture. You will introduce cross ratio. Okay? So how do we count this number of cross ratio? It's easy. So imagine we have NH. To specify my cusp, I need 4n coordinates in 4 dimensions. But these coordinates, they are bound together. There are some constraints. 2 points, 2 neighboring points should be like related to one another. So that gives me n relation among these coordinates. Okay? So this is something that we would not have if we were doing the counting for a local operator. okay, that we have here because we have this constraint. And then there is a number of generator of the gauge group, of the conformal group, which I can use to fix some point. For instance, I could fix this point, I could fix this point, I could fix another one, and so on. So the easiest way of counting is like this. So what we gain is 3n minus 5. 3n minus 5 what? 3n minus 5 quantity coordinates that we could not fix, which are called cross ratio. Yeah.
Should be conservation or not?
Yes, there is. It's included in. So momentum conservation in the scattering amplitude essentially is telling you that the object is closed. You add up all the momenta and they just sum up to 0. Okay. I'm also counting here translation, if it was a question. Translation in the dual space allow me to remove a few of this coordinate here. Okay. So this is a number of cross ratio. In particular, let's look at 6. Let's say 6. So we have 3 cross ratio. So where are these cross ratio? Well, let's draw an hexagon like this. So we could pick, for instance, this point, this 4 point. And that's not what I want to do. This is not very smart. Oh, sorry, that was what I want to do. Yes. Then what I can do is I can take this distance here, multiply by this distance, and divide by the cross distances. Let's say 1, 2, 3, 4, 5, 6. So my first cross ratio that is conventionally called U2, okay, will be x26 squared times x35 squared divided by the cross distances. x25 squared, x36 squared. Okay? So this is a quantity which is conformally invariant, and so it's telling me some information about the geometry of my object up to conformal transformation. Then you can move this picture around by doing some cyclic reordering, and you can construct 2 other cross ratios, U1 and U3. And then you can convince yourself that there is no other. So indeed, there are 3 cross ratios that we can construct for an hexagonal Wilson group. Okay? So we jump ahead to n equals 6, but what about n equals 5? So n equals 5 give us 0 cross ratio. This means that the pentagon is totally, it's a unique object if you want. If you choose one, I choose another one, there is a conformal transformation that relates them. So whatever pentagon you start with for computing this vacuum expectation value, I should get the same thing by using my pentagon, because they are conformally equivalent to one another. Okay? So we are trying to learn a lot, because it means that this object cannot depend on anything. If you think about it, it cannot depend on anything, because it has no kinematical degrees of freedom. And this is also true for 4. But for 4, we get this funny result. We get -3. So with this is smaller than 0, so it means that we don't have cross ratio again. But the reason we get -3 here, I don't know if anybody has an idea why we get something negative here? No? So you should remind you of the way Osborne counted the degrees of freedom for a 3-point function. Took the number of points, multiplied by the dimension, subtracted the number of generators in the conformal group, but then he added up something to it. Okay? He added up the symmetry that live invariant the 3 point. So you can always put 3 point on a line, and then this line has natural symmetry. If you rotate the direction transverse to the line, you are doing nothing. Okay? So this counting was a bit too fast because we did not take into account the fact that our object could have some symmetry. So some generator could just do nothing. Okay? So this is not happening for 5 or 6 or higher, but this is happening for 4, and this is reminiscent of our previous discussion, which is that 4 point is the same, 4 cusp is the same as a single cusp, okay? And the single cusp has some symmetry. We have this boost and dilatation that live invariant our object. So we have this d sigma and d tau, which I have introduced earlier, which leave our object invariant. And beside it, because our object is living in a 4-dimensional space, okay, there are also 2 extra directions that I am neglecting when I'm drawing stuff on a blackboard. And I can rotate these 2 directions. That does not change my object. So we are finding -3 because the square Wilson loop has 3 symmetries, which commute. Okay? This is d sigma that you can think move line. There, you can imagine that there are some lines, some fiducial lines that I will draw. When you do d sigma, you don't change anything, but you move the line around inside. Okay? And there is a d tau, which do the same, but move the line from bottom to top here. And then there are this extra direction, which I cannot draw, but they're outside of the blackboard, which provide me some angle phi for the O2 rotation, which give me a d phi. So this is going to play some role later on, the fact that the square has this particularity that it has this symmetry. And again, this symmetry, when you think about them from the string theory point of view, at least for the more kinematical one, sigma and tau, they are no more than the symmetry of this background. Okay? Again, we found previously that our object in the string setup is just this Euclidean 2-dimensional space. The fact that it has a boost symmetry is an accident of strong coupling, but the fact that it has this symmetry under shift of sigma and tau, meaning that there are 2 infinite directions where I can shift my object around, is not accidental and is there at any coupling. Okay? So this is an important property of this background. Okay? So now, if it were not for the fact that our object has actually divergences, the conclusion would be that the vacuum expectation value of the forecast Wilson loop, or what we call the square Wilson loop, this Wilson loop, is a constant, because it cannot depend on anything. And the same for n equals 5. So the first case which is interesting is n equals 6, because then it can be principal. It's not clear whether it will or not, but as you might guess, it will. It can depend on the cross ratio. So it can be described by a rather complicated function of this u1, u2, u3. And the goal then would be to compute this function explicitly as possible. But the truth lies a bit somewhere in between, because we have these divergences in between trivial and complicated, well, closer to trivial, which is because we have these divergences, actually the object needs to be defined with some cutoff, and this breaks the symmetry, and so it can acquire some sort of anomalous dimension on the distances, like for instance S and T, okay, which define this object from the metric point of view. Okay? But what is very nice about the Wilson loop description is that these anomalies are very well understood. Okay? They are localized close to this cusp again, and then one can derive a kind of improved version of the consequence of the conformal symmetry, which goes under the name of anomalous conformal world identities. Okay? So this is just usual conformal world identities, but taking into account that we have divergences localized at the cusp. And this way one can derive equations which are of the same type as usual, like for instance the K generator, the conformal generator K, annihilator object, up to a simple term that comes from this anomaly, and that we know exactly. And when you try to solve for this equation, so first you know that there is no homogeneous solution to this equation because we don't have cross ratio, so we cannot form homogeneous solution. And the particular solution is nothing else than the BDS ansatz. Okay? So the main conclusion, the first conclusion that we are getting here, is that log of Wn is BDS because our object has divergences, and BDS essentially take care of these divergences. So BDS n plus what is called the remainder function, which is what is not related to these divergences, which is a finite piece, and which is conformally invariant, meaning that depends on the total number of cross ratios. Okay? which means, as a corollary, that n equal to 4 is solved. This piece cannot exist, or it's just a constant, and this constant is something which is not completely something that we could fix by some sort of argument. It's not important. For n equals 5, again, no cross ratio, so the problem is solved. And now the question is whether for n equals 6, this remainder function it gets activated somehow by in the gauge theory. What we know by definition, given that this BDS correctly incorporate one loop computation at least for any n, this should start at 2 loop. Okay? And we know that this cannot be totally trivial because at least at large n and at strong coupling, Aldai and Maldacena gave us some evidence that indeed there should be something which is not captured by BDS, and this is just a rephrasing of this. Okay. So in the simplest case of n equals 6, people did explicit computation at 2 loop, and indeed they found that this remainder function is there. Okay. So now the new problem becomes, can we compute this remainder function, which are function of this conformally invariant quantity. Okay, so that's the main step. So I hope at least, perhaps it's a bit too technical, I don't know, but I hope at least that you can appreciate the kind of improvement, starting from the very beginning, where we knew almost nothing except for the fact that there is a kind of bosonic quantity that can depend on all Mandelstam invariant, and beside it has some infrared divergences in it. So here we kind of solve the problem of the divergences through BDS, and we also understand that the finite part of the result, the piece that we now care about, is not some random function of all the possible Mandelstam invariants that I can form. It is a function of some particular combination of this conformal invariant, namely the possible cross ratio that characterizes Wilson. So in between, we made a kind of huge reduction of the complexity of our object, even though it was probably not easy to appreciate. But now it seems that we took into account all what we could take into account using conformal symmetry and this gift, which is this scattering amplitude Wilson loop duality. And the question is how to compute this quantity using integrability. Okay? I think I still have 10 minutes. No? Yes? Okay. So during these 10 minutes, I will introduce the so-called OPE for Wilson loop. Maybe I will keep this. So the idea of the OPE for Wilson loop is very similar to the OPE for correlator. So once you reach this stage where you understand what you are supposed to compute and how to parameterize it roughly, the question is how do we get explicit expression in terms of this cross ratio? So this is the same problem as if you take an endpoint function in the CFT and you want to compute this endpoint function. You know that it's going to be a complicated function of whatever cross ratio you can form, but concretely, how do you address the problem? So Osborne tells us that, at least in principle, you can always find a solution by using the OPE. So for a 4-point function, for instance, if you take a 4-point function of local operator, you know that one way of computing it is to do the OPE expansion in this channel. So replace 1, 2 by a sum over an infinite set of local operators that provide you a basis. Then propagate up to the top, where you compute the 3-point function with whatever is at the top. So the information that you need here are whatever can propagate in the middle, which is provided by the spectral data, the scaling dimension and spin of the operator, and the 3-point function, which are dynamical quantity. So let me call what is flowing in the middle psi. Then I want to know the scaling dimension of psi and the spin of psi. And then I also need to know the 3-point function C1 to psi, C3 for psi. Okay? And in 2 dimensions, just to simplify a bit the algebra, to avoid this complicated conformal plot and whatever, I could write this partial wave more than conformable. I could write that it is a sum over psi of C1 to psi, C3 for psi. Times some cross ratio Z, whose modulus coupled to the energy, and the ratio or angle coupled to the spin. Okay? So if you know your spectrum, and if you know the 3-point function, you have in principle an explicit form, no, not explicit, but you have, in principle at least, a representation for your object. And what is especially nice about it is that it does not rely at all on perturbation theory. This is true in any CFT, and it's regardless of whether your CFT has a marginal parameter, which you can tune to get some weakly coupled regime. Okay? So the one nice aspect about this approach is that it is non-perturbative. So if it applies at weak coupling, in our case, it will also apply at strong coupling. What remains to be done is to understand the spectrum. This is what Collier told us, and understand this 3-point function, which is what Pedro will talk about. But in our case, we are not really dealing with this problem because it's not a closed string problem that we're considering, but it's more an open string. But still, there is a huge analogy. And if you take, for instance, the hexagonal Wilson loop, which has free cross ratio, one way of thinking about such an OP for this object will be to engineer a limit where we are essentially approaching a problem that we know is totally solved, which is, for instance, this collinear limit. If I take this guy up and this guy down, such that my Wilson loop reduced to a square. Okay? So this is a collinear limit because I'm taking this. So I'm taking here what might look like as a simultaneous collinear limit, but it is conformally equivalent to a single collinear limit. It's irrelevant. I'm just trying to do this symmetrically to simplify the picture. But it's a collinear limit because you see two edges become collinear, and so add up to a single edge. So what is nice about it is that this object we don't know, but this one we know exactly, because it is fixed by conformal symmetry, as we have just seen. Okay? So the idea will be to use this object as a sort of background. Okay? So if you want to think about it, you could do a conformal transformation such as to hide these two edges, the bottom and top edge, and then what we are describing is essentially two infinite lines, okay, which you can think as being the trajectory of massless quark and massless antiquark. So if you cut at a given time, what you have is this pair QQ bar, which source a flux around them. Okay? So that's the very same kind of object that Collier discussed last time. Discussed for Wilson loop, you can map to a system of quark-antiquark. The main difference is that in our case, the quark and the antiquark, they are traveling at the speed of light. Okay? This is the main difference. And this flux here is like a 1+1 dimensional background. Okay? This flux is nothing that the holographic dual of this string here, if you want. You can either, if you prefer, think in terms of the string, which is the gravitational picture of this flux, or you can think directly in terms of this flux if you prefer. It's totally the same. But it's essentially a 1+1 dimensional background, which has schematically again this sigma direction here and this tau direction here that correspond to a shift in space and time. Okay? So we see that we start having a nice background as a starting point, and then if we want to go off it, which is eventually what we want to do, like here, this we could imagine that it starts with the identity, you cut here, you get 1. So this is trivial, that's something you know. But then you will have more complicated things. In particular, you will have the lightest operator in this channel that you will have to consider, and so on. So in our case, what controls this deviation, as you might start to understand, is that we are flattening this direction, we are taking a collinear limit. If we want to go slightly off it, it's essentially equivalent to putting some insertion on this line. So you can imagine that you have these two bumps, or two two cusps that you're flattening, and if you get the exact flattening, you get nothing. But if you go a little bit off, you still have some leftover of this cusp, which is materialized by the insertion of some field. Okay. In particular, it could be some component of the Faraday tensor, F mu projected along this like direction, and perhaps some perpendicular direction, like some n perp mu. And you will have the same at the top, which for the matching of quantum numbers. So this is the main idea, is that when we keep going, then we will have more particles, and so on, which is equivalent to exciting this flux tube. Okay. So Collier did not mention that there is perhaps he did, but I forgot, that there is an excited version of the TBA that he mentioned that also describe fluctuation on top of his particular quark-antiquark configuration. Here is something similar. By putting some insertion at the bottom and top, it is like putting some specific boundary condition at past and future infinity on this flux tube, which I schematically think about as being roughly filling this square. Okay, so here essentially what we have is that we have this flux tube and a small bump propagating on top of it, a small excitation. Here we will get two of them, and so on. And as you might guess, the problem that we are facing is to understand the spectrum of excitations that we can have on this flux tube, understand what are the scaling dimensions. There are scaling dimensions here that should appear somewhere here coupled to the geometry. If you parameterize things properly, it coupled in a rather simple way. So there will be some E of this excitation. There will be some momentum, because now we are dealing with an open string and we have this symmetry. We can move things from left to right, which is the same as having a momentum at our disposal, or from bottom to top, which is the same as having an energy. And there is also some angular momentum that couple to this phi. So this tau sigma phi, they are just a very convenient parametrization of our cross ratio U1, U2, U3. And they have this nice interpretation that the collinear limit is the limit when tau is very large, which effectively suppresses the contribution of AV excitation. Okay? So tau very large means essentially stretching a lot this segment of the hexagon, which is conformally equivalent to flattening the object. So this is the collinear limit. So because of this analogy that I've mentioned, this picture of computing complicated Wilson loop by taking their collinear limit and reducing them to smaller object and simpler object is called the OBE for null polygonal Wilson loop. And it was proposed by Aldai, Gaiotto, Maldacena, Sever, and Vieira. Okay? So this is the background that we were, or the picture that we were looking for. It might not be yet clear to you, but now that we have this at our disposal, we have a 1+1 dimensional description of our object, in which the rules of the game are now relatively clear, and parallel the problems that people have been facing and are now facing for clustering, which is to understand our spectral problem, characterize the space of all possible flux tube excitation, extract their energy and momentum or their dispersion relation, and eventually extract also this more dynamical information here, which has to do with this three-point function. So in this formulation, the problem is non-perturbative from the very beginning, and it starts mainly like a problem that can be addressed using integrability because of this 1+1 dimensional structure that we have just unraveled. So in the last lecture today, I will tell you how to put an extra structure to this picture and make it completely constructible using integrability. Okay? So now, well, now is to make sense of this infinite series and also compute all the quantity as function of the coupling, such as to be able to describe our problem all the way from weak coupling, where we should expect to make contact with the gauge theory, and strong coupling, where we should be able to recover this minimal surface description. Thank you.
I'm a bit confused here about phi sigma tau. You said before that they are related to symmetries of the square.
Yes.
And now you said they are related to 3 cross ratios of the
Okay, yes, because I did not explain one step. So there is one more step. Okay, so let me give you a bit more of information that will show up later. So here I was trying to give you essentially the physics or the philosophy of the program. Then, of course, the first thing that you want to do is to try to set it up in a more rigorous way. And in particular, this means defining properly what you mean by this tau, sigma, and phi. Okay? Intuitively, it is the idea that you create an excitation somewhere on this background which gets annihilated somewhere at the top. So it will propagate over some time and over some space on the flux tube, okay? And get twisted a little bit in this extra direction because your object is twisted. Okay, so that's intuitively. In practice, if you try to make it more precise, what you will do is to add some extra line on your problem, which you define to be light-like, such that they are completely gauged conformal invariant quantity. So you take a cusp and you draw a light-like trajectory that hits the opposite edge. Okay? You do it once, and then you go to the top edge and you do the same. Okay? This way you are decomposing your object into square. Okay? This is something very welcome because the square we understand. Now the picture is that to generate an object which has this U1, U2, U3, we pick some hexagon, some reference hexagon, and then we use the symmetry of the middle square here. So this guy has free symmetry. D sigma, D tau, D phi. Okay? These free symmetry are no more than the conformal generator that leaves this square invariant. Okay? In particular, if it will not leave the rest invariant. Okay? It is just the symmetry of this square. Now, if I use this symmetry and act on all my points, I am doing nothing because it's a conformal transformation. But if I do something more intelligent, I can use the symmetry of this square and act on the bottom. So these 2 points are shared between the top and bottom square, so they will not move. But this point here, they will move. If I use the symmetry of the middle square and act on everything which is at the bottom, these 2 lines will move. And in particular, there will be a direction that this point here will move like this. So this corresponds to sigma modification. This point here will move like that. That corresponds to tau. And then there is this angle phi, which I cannot depict. Okay? So if you use this kind of trick, then you have a direct map between the action of your group element and the cross ratio. Okay, this map you can write explicitly. The simplest one is this one. U2 is equal to 1 divided by 1 plus exponential to tau, which is telling you that taking tau to infinity, which is what we were doing here, corresponds to U2 going to 0, which is indeed what people call the collinear limit. Okay? So that might be clear somewhere. So U2 going to 0 means one of these 2 distances going to 0, which means that either 2 becomes light-like separated to 6, or 3 to 5, or both simultaneously, which indeed, if this guy is light-like separated to this one and also to that one, these 3 lines should be collinear. Okay? So by using the symmetry of the square in a good way, we can replace this cross ratio, which are conventional, but whose physics is not always clear, by something which, at least in our setup, from our point of view, has a clearer understanding. Okay? Because it is conjugate to what we want to call the energy on the flux tube, the momentum on the flux tube, and the angular momentum. Okay? So during the next lecture, I will explain how to put on top of this picture an extra layer, which allows us to also understand what are the equivalent of this coefficient function for which gives us the amplitude for creating a particular flux tube excitation. Okay.